Okay, so here we look at a sample problem. So it says two long parallel wire carrying current I1, I2. So here there are two currents. This I1 is pointing out of the page, and then this is pointing into the page. Okay, so I1 and I2 in opposite directions. Okay, so it also assumes that it is a infinitely long wire. Okay, so what are the magnitude and direction of the net magnetic force at point P? Okay, at point P, assuming the following values: I1, I2, and D. Okay, so this is D. This is a right angle triangle. Okay, so yeah, so we would like to find the B field at this point. Okay, so actually we can just simply use the equation which we have before. So actually the one is like B1 equals mu 0 I1 over 2 pi, and actually this is capital R rather than small r, so just the distance from the point to here. Okay, and actually also B2 should be mu 0 I2 over 2 pi capital R. Okay, so both of them are the same, but of course the direction of them are different. The direction of them are different. So actually we need to use the right hand rule to determine the direction of the B field. Okay, so for example, I1. Okay, actually we can just try to draw a circle like this. Okay, the center of the circle is of course at this point, and then the radius is capital R. The radius is capital R. Okay, so we can draw a circle, and then we can use the right hand rule to determine the B field at this point. Okay, so you can use a thumb pointing out of the page, which is the direction of the current I1. Okay, and then your forefinger will be in this direction. Okay, so this is like counterclockwise. So which means that at this point it should be pointing to the top left. Okay, so you can see B1 here. Okay, so next we can also determine the direction of B2. Okay, so we can also draw a circle like this. Okay, so the center is at the point I2. Okay, actually I cannot draw a good-looking circle because we don't have enough space here. So okay, so it doesn't really look like the center, but of course actually I2 is the center of this circle. And then also using the right hand rule, and then you use your thumb follow the direction of the current I2. Okay, so this time the I2 is pointing into the page, so you use your thumb pointing into the page, and then your forefinger will be in this direction. Okay, which means that this is clockwise. Okay, so at this point B2 will be pointing to the top right. Okay, so B1, B2. Okay, so this is a right angle, so which means that B1 and B2 also perpendicular to each other. Okay, which means that the total B is like B1 square plus B2 square, and then take the square root of the whole term. Okay, and also for this R is just like D over square root of 2, because this is just a right angle triangle, and then these two sides are actually the same, which means that R should be D over square root of 2. Okay, so nothing special. So it is like 5.3 over square root of 2, which is 3.75 centimeter. Okay, so here we can try to calculate the B, which is like mu 0 over 2 pi R, and then square root of I1 square plus I2 square. Okay, because this term square and then this term square, add them together, and then mu 0 over 2 pi R are the common factors. So this term will come out, and then the remaining term I1 square plus I2 square, and then take the square root. Okay, so this is 4 mu. 4 mu is mu 0. Mu 0 is 4 pi times 10 to negative 7 over 2 pi times r. R is 0.0375. Okay, and then times square root of 15 square plus 32 square. Okay, like this. Yeah, so this is actually 118 micro mu Tesla or micro Tesla. Okay, so this is the magnitude. This is the magnitude. Okay, ask you the magnitude and also the direction. Okay, so here we would like to find the direction. What is the direction of this one? Actually, you can just decompose it, B1 and B2 along the x-axis and y-axis, and then add them together. But it makes things more complicated. So actually, we can just try to find phi, because this is this triangle is is not parallel to the xy axis. But actually, it is easy to find phi because B1 over B2 is actually tangent of phi. So we may be able to find phi to be arctangent of B1 over B2. Okay, after we find phi and then we add it by 45 degree, and then it will be the angle from the x-axis. Okay, so usually we will consider the angle from the positive x-axis to this line. Okay, so actually phi will be arctangent of B1 over B2. Okay, so B1 over B2 will be nothing but arctangent of I1 over I2. Okay, if we divide B1 by B2, okay, so all the common factor will cancel each other, and then the remaining term will be I1 over I2. Okay, so this is nothing but arctangent of 15 over 32. Okay, so this is 25.1 degree. So finally, this angle, we may call it theta. This theta will be 45 degree plus 25.1 degree. So which is 70.1 degree. Okay, from positive x-axis. Okay, so this one is not that difficult because we just need to find B1 and B2, and the only thing we need to know is that the B field is a vector. Okay, so which means that when we try to add them together, we need to consider whether they point to the same direction. Otherwise, we need to consider it's a vector sum. Okay, so next we talk about the force between two parallel currents. Okay, so in the last chapter, actually the last part in the last chapter, I mean chapter 28, we know the other version of the Lorentz force will be like if we have a current in the B field, if they are not parallel, they are not parallel, there will be a force acting on the wire. Okay, so now we know actually the wire will generate B field. Okay, the wire will generate B field like the B field line will be like a concentric circle, 同心圆. Okay, so which means that if we have parallel current, either the current pointing to the same direction or opposite direction, okay, there will be some force acting on them. Okay, because if we have two current, okay, for example, this one going to the same direction, which means they are parallel. Okay, so this current will generate the B field at this point or at the wire B. Okay, which means that okay, this wire will be actually in the B field, will be in a external B field. So this B field is not parallel to the current, so there will be a force acting on it, and vice versa. This current will also generate B field here. So this B field will make this current, okay, so will interact with this current, and then there will be a force acting on it also. Okay, so these two forces will actually point to opposite direction. Okay, so it either makes the two wire attract each other or repel each other. Okay, similar to the Coulomb's force. For the Coulomb's force, or they can either attract each other or repelling each other. Okay, this time similar things will happen. Okay, so let's see. It says parallel wires carrying current in the same direction attract each other. Okay, so the key word is like in the same direction they will attract each other. And parallel wires carrying current in opposite direction, they will repel each other. Okay, so that's the quick conclusion. Okay, we'll see why it will be like that. Okay, so first of all, we see the magnitude of the force will be something like this. So just as what I mentioned, we will actually use the like the second version of the Coulomb's force. So which is like the force will be like I times L cross B. Okay, so if it is a vector form, it will be like L cross B. We can quickly find that this is B, this is the direction of B, and then this is the current of I, which means that L is in this direction. Okay, so L and B are perpendicular to each other, which means that for the cross product, L cross B, it will be nothing but L times B times sine of 90 degrees. Sine of 90 degrees is just 1, so we can only have a F to be I times L times B. Okay, so let's see each of them. Okay, so in the last chapter we don't know how to find B, but here we already know how to find B. So here, of course, IA and IB is already a known value. Okay, so IB is a known value. L is also a known value. We consider, for example, this segment is L. Okay, and then we would try to find BA. Okay, so here we also assume that the current are infinitely long. Okay, so are also a long current, which means that here we will apply that BA will be like a mu mu 0 IA, and then 2 pi the distance between them is D rather than R. So here the distance, as much as these two currents are parallel to each other, okay, we denote this is small d rather than small r. Okay, if you denote it as small r, here is 2 pi r. Okay, so this is just a notation. Okay, so here it just means that for FBA, it is the force acting on the wire B due to the wire A. Okay, so this B means the force acting on wire B due to wire A. And actually you can do the same thing like FAB to be like IA and then LBB. Okay, you will get the same value, exactly the same value. You can try it by yourself if you have interest. Okay, so here we can just plug in this BA into here. So you can see mu 0 IA, and then LIB. Okay, so here we will have mu 0 LIAIB, and then over 2 pi d. Okay, so this is pretty much it. So very trivial to get this magnitude of the force. Okay, so you can see that IA and B are symmetrical to each other. So you can clearly see that here we'll have a mu 0 IB, and then here we also have IA. And then so we'll have mu 0 IAIB over 2 pi d. Okay, so very clear that the FAB and FBA will be the same value. Okay, so here we can see that this is the magnitude, and then we can see what is the direction of the force. Okay, so here, suppose IA and B are parallel and then pointing to the same direction. Okay, so IA is from bottom left to top right. IB is also from bottom left to top right. Okay, so here, using the right hand rule, we can determine the direction of BA. Okay, so you use of thumb pointing to this direction. Okay, follow the direction of the IA, and then your forefinger at this point, will be pointing to this direction. Okay, of course this is a 3D graph, so this is just like pointing downward. Okay, so here we can use the right hand rule to determine the direction of BA. Okay, you use your thumb pointing to this direction, your forefinger will pointing to this. FBA will be pointing downward. Okay, and then L just follow the direction of IB. Okay, so L and IB are perpendicular to each other. Okay, so FBA vector will be like L cross BA. Okay, so L cross BA, L is pointing to that direction, B is pointing to this, so FBA will be pointing to this direction. Okay, so which means that, so if IA and IB are going to the same direction, FBA will be pointing from IB to IA, and then similarly FAB will point to the opposite direction. Okay, you can try it by yourself. I do not repeat again, but yeah. So actually, if IA and IB are pointing to the same direction, the two wires will attract each other, just as what here said. Okay, so if parallel wires carrying current in the same direction, they will attract each other. If IA are pointing to the opposite direction, in this case, you also use the right hand rule. Okay, let me go to this side. Okay, so you use a thumb pointing to the direction of IA, and then your forefinger will be pointing to that direction. So which means that BA will be pointing upward. Okay. So in this case, BA is pointing upward. Okay, so here we have L cross B. So FBA will point to this direction, and similarly FAB will point to the opposite direction. Okay, so which means that if IA and IB points to opposite direction, the wire will repel each other. Okay, so it says, so the general procedure for finding force on a current wire is blah, 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 blah. Okay, so yeah, so just as what I mentioned, so I do not repeat. Okay, so here it says, similarly, if two currents are anti-parallel. Okay, so here it just tried to simplify what it tried to mention. It tried to mention parallel as the first case. Parallel means parallel wire carrying the current in the same direction. So it just tried to call it parallel only. And then for the second case, it tried to call it anti-parallel. For this, so we don't try to call it a parallel wire carrying current in the same direction or in opposite direction. For the whole thing, we just call it parallel current. And then for the whole thing, parallel wire carrying current in opposite direction, we call it anti-parallel. Okay, so it just said parallel current attract each other and anti-parallel current repel each other, simplifying like this. Okay. Okay, so here we come to the most important part in this chapter, which is called the Ampere's Law. So just as what I've mentioned before, so Ampere's Law is the second law we learned in the Maxwell equation. Okay, so before we have learned the Gauss law in chapter 23. So here we'll try to learn Ampere's Law. Okay, so here, let's see. Ampere's Law states that, okay, so this is also a integral. Yeah, so this is an integral sign with a circle. So you can expect there is something closed here. Okay, so what is closed? For the Gauss law is a closed surface or a Gaussian surface. This is not a closed surface anymore because this is not dA. For the Gauss law, it is dA, E dot dA. So here is not dA, it is B dot ds. So this is a line integral rather than a surface integral. For the Gauss law, it is a surface integral. So here is a line integral. So a surface integral is like an integral in 2 dimensions. Okay, so this for this line integral is an integration in 1 dimension. But of course, it is more difficult than integration like this fx dx. A little bit complicated than that. It is like if we have probably in 2 dimensions or even in 3 dimensions, we have a path. For example, like this. We try to integrate from the starting point to the end point, from A to B, okay, along this path, and then in the space there may be some vector field, for example a B field, inside the whole space, and then we try to integrate this B dot ds over this path, and then it is called a line integral. It would be something like this. It will be a line integral. So suppose it is a line integral. What we did is similar. So it's just like we try to cut it into small pieces, and then of course you already have a direction. For example, from A to B. Then for every segment, okay, it is just like the tangent line ds, and then follow the direction from A to B. For example, this part is ds, and then for every part you try to find B dot ds. For example, if B at this point is pointing to this direction, okay, and then you try to calculate B dot ds for this part, and then it becomes a scalar. And then for every part, okay, for example in this part, okay, for example this is ds, and then for example B is pointing to that direction. Or for every point you can just simply calculate B dot ds. It's just a dot product or inner product, okay, and then all this part will become a scalar. Then you can just add them together, okay, and then it becomes a line integral. And here, if we have this circle, similar to the Gaussian, Gauss law, okay. For the Gauss law, is like integration of E dot dA, okay. So for this one, it means the surface is closed. So here, it means that the path is closed, okay. So it form a loop like this. Okay, so yeah. So the line integral in this equation is evaluated around a closed loop, okay, a closed loop. Okay, so this closed loop is identified by this circle, okay, called an Ampere loop. Okay, so sometimes we just call it a closed loop, and in this textbook it's just call it the Ampere loop, okay, because it is for Ampere's law. So we call it Ampere loop. Okay, so just a name, so don't be afraid. It just means a closed loop. Okay, nothing else. Okay, so on the left side it is just a line integral for a closed path. Okay, so yeah, so this is pretty much it. And then on the right hand side, it is quite similar to the Gauss law. Okay, so let me try to write it. Try to write it out. Okay, for the Gauss law, it is like epsilon naught equals Q enclosed, something like this. Okay, so here, this surface integral become a line integral. Okay, and then just as what I mentioned, epsilon naught turns it into 1 over mu naught. I mentioned it in the last lecture. So usually when they have some relationship, epsilon naught change it to 1 over mu naught, and then here Q enclosed change it to I enclosed. Okay, of course we just multiply this one to the right hand side. So on the right side we can see mu naught I enclosed there. So actually they look quite alike. Okay, so here we also have I enclosed. For the Gauss law, it means that it means the charge enclosed by the Gaussian surface. Okay, so it only counts the charges inside the Gaussian surface. All the charge outside, just ignore it. Here, as much as this is an Ampere Node, so for example, this is an Ampere Node in this surface. And then, for example, if we have free currents in the space, so I1, I2, and I3. Okay, we also assume that these I1, I2, I3 are all long wire, which means that for this one, I1, it is from negative infinity goes to the infinity and then going out of the page. Yeah, this is going out of the page because this is a dot. Okay, and then this I2 is going into the page from infinity going to the negative infinity to infinity. Okay, this one is going out of the page. So here, if we try to consider the I enclosed of this Ampere loop, only I1 and I2 are enclosed. I3 are out of this loop. Okay, so if we consider the Ampere's law for this Ampere loop, we only count I1 and I2. We don't count I3. And then next we need to determine the sign, the polarity, whether it is positive current or negative current. Okay, how to determine whether it is positive or negative? Still, we are using right-hand rule. Okay, so here it says, this is how to assign a sign to a current used in Ampere's law. Okay, so suppose this is the Ampere loop. And then for Ampere loop, we also need to determine which direction, whether it is a counterclockwise or clockwise. Actually, this is up to you. If you just assume it is counterclockwise, then use it all the way. Or if you would like to assume the Ampere loop is clockwise and still use it all the way, then you will get the same result. It's just like you have negative sign on both sides, and then finally it will cancel. Okay, so for this case, if we assume that this Ampere loop is counterclockwise, okay, so using the right hand rule is like you use your forefinger, follow the direction of the loop, and then your finger will be pointing out of the page. Okay, pointing like upward. Okay, so this is the forefinger, and then this is your thumb. Okay, so this direction is positive. This direction is positive. Okay, this is negative. Okay, so which means that I1 is pointing out of the page. So I1 is positive. I2 is negative because I2 is pointing into the page for this Ampere loop. Okay, so we also try to use right-hand rule to determine the polarity of the current or the I enclosed. Okay, so this is so this is the introduction about the Ampere's law. So the current I on the right side is the net current encircled by the loop. Okay. So mu enclosed means we only count the current enclosed by the loop. Okay. The current outside the loop we don't count, and then after excluding the current don't count, then we need to determine the polarity, and then this is pretty much it. Okay, so here we try to use the Ampere's law to verify what we get before. Okay, so this is actually what we obtained before using the Biot-Savart law. Using the Biot-Savart law, we can really calculate this B field generated by a long straight wire with a current. Okay, so in that case it is similar to what we did in chapter 22, but for the E field. Okay, so we can do segmentation, and then we try to find the DE generated by the small pieces, and then finally we add all of them together, and then we can find the overall B field. Similar for this, we use the Biot-Savart law. We try to cut the segment into small pieces. Every pieces will generate B field at a point, and then we try to add them together. This is what we have done in the last time. So here, we use the Ampere's law to really get the same result with just a few steps, 1 or 2 steps. It's just like in chapter 23, when we learn Gauss law, then we need to know what does it mean by the Gauss law, and then if we apply it, we can quickly know the E field quickly for some specific structure, or usually symmetrical structure. Here is similar case. So for example, here we have a current going out of the page. It doesn't necessarily to be a very thin wire. It may be a wire with a certain radius, capital R. Okay, for this wire, it has a radius capital R. Sorry. But actually this one is not this one is not correct. We need to slightly modify it into something like mu 0 I over 2 pi small r. Yeah, we consider this one. Okay, the distance from the center of the wire to this one is small r. Okay, from here to here is small r. Okay, so we use 2 pi r here instead of 2 pi capital R. Capital R is the radius of this wire. Okay, so here, we also define the red circle is the Ampere loop. And then we just here the current I is distributed uniformly in this wire and then pointing out of the page. So it denoted by this dot inside a circle. Okay. So here we try to define the direction of this Ampere loop to be counterclockwise. Okay, which makes everything positive. Okay, because if this is the direction of the Ampere loop. Okay, you use your forefinger following this direction, and then this direction is positive. Okay, so you will get this current I is positive. Okay, so we use the Ampere's law like this. Okay, so here B and ds. Okay, B and ds will point to the same direction all the way. ds is the tangent line. B is also the tangent line to this circle. So B and ds always point to the same direction, which means that B dot ds, theta is equal to 0. So B dot ds is always equal to B times ds times cosine of 0 degree, so which is 1. Okay, so B ds. So it becomes integration of B ds equals mu 0 I enclosed in this case is I, so we can write it as I, and then B will be uniform. because for the circle, the distance from this circle to the center point will be the same, so B will be uniform, just like what we have, how we use the Gauss law. Okay, so here B is uniform, so we can just put it outside. It turns out to be B times integration of ds equals mu 0I. Okay, so this is the line integral of the circle. For the line integral of this closed circle, which is just like the circumference of a circle, which is 2 pi r. Okay, so we will have B times B times 2 pi r. 2 pi r. 2 pi r is the circumference of this circle, which means that integration of ds is 2 pi r. Okay, equals mu 0I. Okay, so we can just move this one to here. So finally we'll get B equals mu 0I over 2 pi r. Okay, so this is what we got in the beginning of this chapter using the Biot-Savart law. Okay, which is this one. Okay, so this one, when r is larger than capital R, larger or equal to, which means that the point outside the straight wire, okay, we get this expression. Okay, it doesn't really matter whether this wire is thin. Thin means the radius of it is 0, or if it has some radius and then the current is distributed uniformly over this wire. It should be uniformly distributed. Otherwise, B might not be uniform over the circle. Okay, so uniform is still necessary. Okay, so the second case, this is also really important. I hope you know how to derive it. Okay, so here we try to consider the point inside the straight wire, which means that R is smaller than capital R. R is smaller than capital R. So in that case, we try to let me try to draw this one. Okay, so this is capital R. Here we try to assume that this is the Ampere loop. This is the Ampere loop. And then the current I is going out of the page. This is I. And then also we try to define the current is counterclockwise, so I will be positive. Okay, so here, as much as we need to use the Ampere law, Ampere's law equals mu 0I enclosed. Okay, so for the left hand side, it will be the same thing of B times 2 pi r. Okay, I do not go step by step, which is just like going from here to here to here to here. Okay, it just become B times 2 pi r. All the reasons are actually the same as here, although the B is not the same. Okay, so on the right side, mu 0I enclosed. I enclosed is not I anymore because I is uniformly distributed over the whole cross-section area. But the Ampere loop is smaller than the wire, which means that I enclosed is smaller than I. So, but hopefully but luckily the current is uniformly distributed over the cross-section area. So we can simply calculate as I enclosed over this area. This area is pi r squared. And then for the whole I is distributed across pi capital R squared. Okay, so in this case, I enclosed is R squared over capital R squared. Pi and pi can cancel each other. Okay, so this is I enclosed. Okay, so here we have times I. Okay, so this is nothing but I times R squared over capital R squared. Okay, and then finally we can just cancel this r square with this r. So finally it becomes b equals mu 0 I small r over 2 pi capital R squared, okay, which is actually this one. Okay, so which means that if R is larger than the radius of the wire, then the B field is inversely proportional to R. But if R is smaller than capital R, which means that at the point inside the wire, the B is proportional to R. Okay, like this. Okay, so here let's take a look at this sample problem before we have a break. Okay, so here it says the cross section of a long conducting cylinder with inner radius A. Okay, so this is the inner radius and the outer radius. Okay, so the cylinder carry a current out of the page. Out of the page means out of the page like this. This is the I. And the magnitude of the density in the cross section given by J equals CR squared. This is not uniform. This is related to R. Okay, related to R. R means the distance from the center to a point somewhere R. Okay, so for example, if we try to define the Ampere Node here, okay, this is the R. R from small a to small b. Okay. Yeah. So what is the magnetic field B at a point that is 3 centimeters from the central axis of the cylinder? Okay. So A is 2 centimeters. Oh, A is 2 centimeters. B is 4 centimeters. It just asks you C to be R to be 3 centimeters from the central axis. Okay. So which means this Ampere slope is right in the middle. Okay. So so here I enclose should be like integration of J dot dA. J dot dA. So this is the definition of the current. So of course we only know J only, so we need to do some integration because J is not uniform. Okay, and actually J and dA will be parallel or anti-parallel. Actually this is anti-parallel. So for this question it tried to assume that this Ampere loop is clockwise. Okay, so you can quickly find that using the right hand rule. Okay, you use your forefinger going clockwise, your thumb is pointing into the page, but the current is going out of the page. So I will be a negative value, which means that J and dA points to opposite direction. Okay, so in this case, using the right hand rule, you know that dA is pointing into the page using the right hand rule. Okay, so dA is pointing into the page. Using right hand rule you can determine. Okay, so here it is like negative integration of J times dA. Okay, and then we can just put in this expression equals negative integration of CR squared, and then dA for this polar coordinate will be like r d theta. Okay, hope you still remember. Okay, and then for dr it is from small a to small b, and then for theta it is from 0 to 2 pi. Okay, I think this is pretty trivial. I think we have done this thing before. Okay, so here we have a negative. C is a constant, so we can put it outside. And then we all together have r cubed. So integration of r cubed dr, integrate from a to b. And then for d theta, it is nothing but a 1, so we can just forget it. Okay, so from 0 to 2 pi. Okay, so it means that this is 2 pi. This is b to the 4th power over 4 minus a to the 4th power over 4. Okay, so this is nothing but minus c and then b to the 4th power minus a to the 4th power times 2 pi over 4. Okay, so these 2 and 4 can be cancelled, and then it becomes negative c and then b to the 4th power minus a to the 4th power pi over 2. Okay, so this is I enclosed. This is I enclosed. Then we can just try to apply the Ampere's law for this Ampere loop. Okay, so this is integration of b dot ds equals mu 0 I enclosed. Okay, so on the left side, it's similar. B times 2 pi r, and then equals mu 0, and then times negative c b to the 4th power minus a to the 4th power pi over 2. Okay, so we will get something, yeah, we can actually cancel this pi and this pi. Okay, and this move these 2 out to here, so it becomes 4 out in the denominator. So which means that it is actually b equals negative mu 0 c and then b to the 4th power minus a to the 4th power over 4r. Yeah. Okay, so this is negative. Mu 0 is 4 pi times 10 to negative 7. And then times c. C is here. Okay, 3 times 10 to the 6th power. And then times b. B is 4 centimeter, A is 2 centimeter. So this is 0.04 to the 4th power minus 0.02 to the 4th power. And then all over 4 times R is 3 centimeter, 0.03. Okay, so yeah, so this is actually a negative 20 mu Tesla. 20 mu, just erase that. Okay, so the answer is negative 20 mu Tesla. Okay, so it means that here we define the Ampere loop to be like this, and then we get a negative value, which means that finally the B field is in this direction. The B field, of course, for the whole loop, but I don't try to cover the whole circle. Okay, so B field is counterclockwise, because if we define Ampere loop to be clockwise and then get a negative value, and then B should be counterclockwise. Of course, at the very beginning, you can try to define the Ampere loop is counterclockwise, and then finally you will get a positive value, because if you try to, at the very beginning, if you try to define this is the Ampere loop, then using the right hand rule, okay, your DA is pointing out of the page. DA is pointing out of the page. So DA and J will point to the same direction. Then you will get a positive value here, and then it will all the way get this positive value until and then finally you will know B is also counterclockwise. Okay, so it doesn't really matter whether you define it to be clockwise or counterclockwise, as much as you try to determine the positive or negative side correctly all the way, then you'll get the correct answer. Yeah, okay, so this is pretty much it. Okay, I just don't use this page. Okay, so